I'm very happy to be able to explain what I'm doing currently with my collaborators. So as the title says, I'm gonna talk about symplectic foliation in high dimensions, and more specifically about the version of vanishing cycles for this kind of foliations. This is joint work with Klaus, Niederkrüger, and Lauran Toussaint. It's still in progress. Hopefully, it will be out on archive soon. But yeah. So let me start by a short introduction with some basic definitions and motivation. So, by the way, tell me if I start writing too small, too big, or illegible during the talk. This is the first time I'm writing on this tablet. Okay, so let me first start by recalling what foliations are and so on. So we work always on manifolds of odd dimension, 2n+1. This is a smooth manifold, oriented, and closed. Then we look at foliations, which are hyperplane fields. So we write them as kernel of one form, nowhere vanishing on our manifold. So this is a foliation. We have the following condition. So alpha wedge, the alpha needs to be 0 everywhere. Okay. So if it's the first time that you see this, it might not tell you much, but so let me make a remark that tells you actually what these objects look like locally. So locally, foliating manifold. I mean, here, okay, I'm always, for those of you who know, these are always codimension foliations, okay. I will always talk about codimension 1 foliations throughout the talk. So this is locally, we have a normal form, which is as follows. So this is R2n+1 with the kernel of the one form dz, where here I'm using coordinates x1, y1, xn, yn, and z. Okay. So essentially, this tells you that so like here you can look the partition of R2n+1 by, I mean, the tangent bundle to this is just given by you have these some manifolds, z equal constant, which are always tangent to this distribution, to this foliation. So essentially, we are saying that a foliating manifold is kind of the same as partition of M in some manifolds of codimension 1. These are called leads. Okay, so this is the geometric picture to have in mind with foliations. And okay, so this the style of foliation has a very long history, but there's one result in particular which I would like to focus on. This is a result due to Novikov from 65. It's in dimension 3. So it says that if we have a foliation which is taut, I'm gonna say what it means in a moment, on a 3 manifold, this 3 manifold, then this has no vanishing cycle. So I'm going to tell you in a second what vanishing cycle means as well, but let me just point out that in particular, this implies the following. So every loop in M, which is transverse to F everywhere, actually injects in the pi1 of M. So in particular, if we have a taut foliation on a 3-manifold, the 3-manifold needs to have, so this is Z, of course. So the 3-manifold needs to be, the pi1 needs to have an infinite, an element of infinite order. And okay, so let me tell you what taut means. So taut means that there is a loop. Okay, it's not the same gamma as in the statement, but transverse to F and intersecting every leaf. Let me tell you what the vanishing cycle is now. So let me tell you, let me do it here. I need a bit more space. So this is a definition in dimension 3, okay? I mean, there's a definition, I mean, this taut, this definition of taut actually holds, I mean, you can define this in any dimension. This definition of vanishing cycle, there are some definitions of topological vanishing cycle in high dimensions, but they're slightly different. But so this, I'm talking about the dimension 3 case. So this is a map. So an embedding of the disk inside the manifold, so the foliating manifold, so that the induced foliation on the disk looks like this. So we have our disk, and the pullback foliation must look like concentric circles. Okay. So it's singular at the center, but non-singular otherwise, and just foliated by circles. Okay. And so the boundary is a leaf as well. And we ask that if we look at the image of so this is S1R, I don't know, this is the circle. Of radius R in the disk. So these are the leaves, and oops, sorry. So leaves are this S1R. And this we want it to be contractible in the leaf of the foliation F in which it is contained. If and only if R is smaller than 1. Okay. So R equal 1 is not contractible in the leaf where it is contained. So let me do the typical example of a vanishing cycle. It's given in the rib component. So there's a foliation of S1 times D2. Okay, we can close it up to a foliation of a closed manifold, but this is not important. So this manifold is not as boundary, but so the foliation to look at is given as follows. So I'm thinking of S1 times times D2 as well, as disk times interval, where I quotient the top and the bottom. And how does the foliation look like here? Well, it looks as follows. So if I take a section, this is a section. I mean, if I put coordinates here, for example, x, y, and z, this is a section x equals 0. The foliation there just looks like this. Okay, so it's just accumulating essentially on the boundary component, which is itself a leaf, okay? And now, okay, I described it on a section, but in fact, this foliation is invariant under rotation along the z-axis, okay? So what it ends up looking like here in this picture is basically just a bunch of planes, which are somehow asymptotic to this boundary leaf, which, yeah, to the boundary, which itself is a leaf, okay? So the boundary leaf is a, let me draw it in red, is a two torus, whereas the stuff inside are twos, okay? And in particular, we can see here a vanishing cycle. So if we just look at this disk, for example, this transverse disk, this is a vanishing cycle. Because the foliation is exactly given by concentric. I mean, here you have to imagine that all the leaves are like this. So the foliation on the disk is exactly given by concentric circles. And moreover, all these circles are contractible in the leaf where they're contained, only if they are in the interior of the disk. Okay, the boundary leaf, this one, lives on the two torus, and there it is not contractible. Okay, so this is the kind of picture to have in mind. Okay, in fact, it's not a coincidence that I'm doing this example, because every time we have a vanishing cycle in dimension 3, this implies that there's a rib component like this. So this is called the rib component. But okay, this is not a trivial result. I'm just mentioning it so you know. Yeah, so these are the objects in this result, and the idea is exactly that. So this Novikov statement tells you that this class of foliations is nice in the sense that they tell you something about the manifold where they live. Okay. In particular, it tells you that exactly the pi1 must satisfy some property. Okay, it must have an infinite order element inside. So the idea is a bit to try to generalize this to high dimensions. So the question is, is there a class of foliation in high dimensions which tell you something about the topology? Topology of the ambient manifold. Okay. So this is the motivating question for this work. And okay, so let me mention straight away that taut foliations in high dimensions are not the right thing to look at. So there's this result by Meunier. This is 2009. Who says that so in dimension at least okay, let me state it like this. So every hyperplane field, which just means the kernel of a nowhere vanishing one form, is homotopic in the space of hyperplane fields. Sorry, I forgot. Okay, every hyperplane field on what? On a manifold of dimension at least 4. This needs to be at least 4. Okay. So the statement is that every hyperplane field on this high dimensional manifold is homotopic to a taut foliation. Okay. So in particular, if you want to, well, if we are searching for a class of foliation that give you some restrictions on M, well, this is not the right class, right? Because we are saying that whenever we have a hyperplane field, then we always have a taut foliation, which is not true in dimension 3 because of this Novikov statement. Okay, so what are the candidates to look at then? well, these are symplectic foliations, right? So then, okay. Well, in fact, strong symplectic foliation. So let me let me define what these are. So let me first recall what a symplectic structure is. So if we have an an even dimensional manifold oriented, we say that the two form on this manifold is symplectic if the maximum exterior power is a volume form and it is closed. Okay. Then we try to put these kind of structures on, we consider these kind of structures on the leaves of a foliation. So if we have foliating manifold, so this is of dimension 2n plus 1, the foliation is as I defined it before. This is a foliating manifold. And we have a two form on M. We say that it is a leafwise symplectic. Well, if omega restricted to every leaf of the foliation is symplectic on the leaf. Okay, so recall that these leaves are two n-dimensional submanifolds in M. Okay, so this makes perfect sense. And okay, and we call F omega symplectic foliation. Okay. Okay, so these are symplectic foliations. Here on the top I wrote strong symplectic foliation, so let me define them. So F omega symplectic foliation on M is strong if we have the additional condition that omega is closed on M. Okay, so this is not included in the definition of symplectic foliation, because there we're just asking that omega on the leaf is symplectic. So this just means that d omega restricted to the leaf is 0. Okay, but it needs not to be 0 on the transverse directions somehow. Okay. Yeah, so this is really an additional assumptions that you're making here. Okay. So okay, these are the objects that we look at. So before explaining you why these are somehow the better candidate to look at when we are trying to understand this problem of like finding foliations which give some topological restriction on M, I also wanted to mention that these objects actually arise naturally not only from the perspective of foliation theory, but also from contact geometry, where there's an open problem in high dimensions of finding approximation results of foliations by contact structures, and it turns out that in that setting as well, symplectic foliations are kind of the right candidates to look at. And they also arise in Poisson geometry, where somehow this symplectic foliations just correspond to a special class of Poisson structures. Okay, and whereas usually in Poisson geometry, it's really geometry, so people study things locally. For this kind of objects, you can somehow have arguments have more global arguments, right? So you can somehow say things topologically. And that's why it's interesting from the Poisson perspective, in a sense, because you can use other kind of techniques to say something. Okay, so this was just some propaganda, let's say, of why people should be interested in this kind of stuff. But so let me tell you why these are the right candidate to look at for this problem. So, okay. In other words, let me mention some results about these objects. So, there's okay. The first result I want to mention is one by Bertelson. So she proved an existence H principle for symplectic foliation on open manifolds. Okay, there's some assumptions here that I'm not saying, but so this tells you in particular that at least you know that these objects exist in on open manifolds under some natural assumptions, let's say. Okay, so these objects are not. I mean, you know that there's plenty of them, right? And then so it makes sense to actually study them because it's a class which has lots of things. But on the same, I mean, on the other hand, okay, here I mentioned open manifolds, but for closed manifolds, the situation is pretty different at the moment. So the existence problem is not, let's say, is not well understood for closed manifolds. So what I mean by this is that, for example, there's an important result by Mitsumatsu, which is among those that kind of started, kind of raised interest for this kind of object as well. He proved that S5, the 5 sphere has a symplectic foliation. Okay, but already it's an open question whether S7 or higher dimensional spheres have. Okay, and well, techniques by Mitsumatsu can be pushed a bit further. So I did this in joint work with Lauran and Toussaint to 5-dimensional manifolds, which are simply connected, and for most of them you can find symplectic foliations. Okay, but still the techniques of constructions are pretty specific. They're related to finding good open books on the manifolds. So it's not obvious. I mean, it's a big open problem that whether spheres, whether yeah, in higher dimensions you can actually say something in general as well. There are of course some constructions on. I mean, for example, product of S1 times a closed symplectic manifold obviously always admits a symplectic structure, a symplectic foliation, and there are some constructions like round fiber sums and so on. But yeah, so we are far from having like an existence H principle on closed manifolds, for example. Okay. Yes, and so now what I wanted to say is that for strong symplectic foliations, well, some of these constructions that we have for symplectic foliations give strong symplectic foliations. So we have like a non-empty glass here as well, but it's not clear to what extent we can find H principles for this, or like on if they exist on every manifold. For instance, S5, this S5 here, this symplectic foliation here is not strong, and it's an open problem whether S5 admits a strong symplectic foliation. And so the reason why this exists even less often is that so again we can say that these are somehow more rigid in the sense that we can use for them techniques, so rigid techniques from symplectic topology, meaning by this pseudo-holomorphic curves and Donaldson theory. And yeah, so because of this fact, so there are some partial results in this direction, but mainly because of this fact, the hope is that one can get some topological restrictions on M if it has a strong symplectic foliation. So that actually this class plays the role of the taut foliations in dimensional 3, the dimension, I mean, that I was talking about before. Okay, this Novikov statement. And yeah, so this is the hope. There's one result, one known result by Venugopalan, which seems to be saying that this is maybe not the case, but so it says the following. So she has an example of a strong symplectic foliation, which has, of course, in dimension, I mean, on some manifold of dimension 5. Okay, she can construct on any higher dimension than 5. So let me write it. At least 5. So there's an example of strong symplectic foliation, which has a vanishing cycle. And moreover, and so that there is a loop transverse to F and contractible in M. So here the definition of vanishing cycle that I'm using is just the obvious generalization of the previous one. So I just mean that there's a disk which is foliated in this way, and so that the boundary leaf is not contractible in the leaf where it is contained, whereas all the leaves in the interior are. Okay. Yeah, and the fact that there's the loop transverse to a foliation and contractible in M tells us that, well, we cannot expect the obvious generalization of Novikov theorem for this kind of foliations, okay? This cannot hold. At least with the same definition of vanishing cycle, okay? And looking at the pi 1. So, okay, one thing that I realized I didn't mention before, but it's very important, is that this definition of foliation, of strong symplectic foliation, so on a 3 manifold, F omega strong symplectic is equivalent to F taut. Okay, so actually this is really an extension of the definition. Okay, it's not something weird and completely different. So meaning if F omega is strong symplectic, then F needs to be taut, and if F is taut, then there is an omega on F, which makes it a strong symplectic foliation. Okay. So these are kind of natural extensions of taut foliations in dimension 3. Okay. And okay, so I was saying that this result by Venugopalan says that, well, we cannot expect an obvious analog of Novikov in high dimensions for these foliations, but kind of the point of our work, of our joint work, is that in fact, this is in progress. in fact, one needs to consider vanishing cycles, not according to this topological definition, but like a notion of vanishing cycle, which is somehow detecting the omega on the leaves. So, okay, I'm going to write the statement. Strong symplectic foliations have no what we call symplectic vanishing cycle. I'm going to explain this in a second, what it means. But yeah, so one comment is that we are not at the level of giving topological restrictions on M, okay? But as you will see in a second, this fact suggests somehow that one might be able to find topological restrictions on M but not on the pi1 level, but maybe on the pi n level, okay? Or on n's homology classes of degree n, okay? So this is not, we don't have any result in that direction. We are still trying to figure this out, but this is kind of a bit, yeah, a bit the idea that, okay, there's no obvious Novikov theorem in high dimensions, no obvious generalization, but there maybe is if you look at the right object, at the right topological properties of M, right? So this is this is the result I'm gonna talk about, and yeah, so we have some examples of foliations which have these symplectic vanishing cycles, but that are not known to be not strong according to other previously known obstructions to strongness, okay? So this is kind of a really distinct obstruction from the previously known one to strongness. Okay, so are there questions about this or? Okay, then let me go and define what these symplectic vanishing cycles are. So let's pick a symplectic foliation on a manifold of dimension 2n+1, and let's pick a manifold of dimension n-1 closed. This is kind of the model for our, I mean, you will see in a second, but this is the model manifold for our symplectic vanishing cycle. So we consider C, stands for cycle. So manifold of the form disk times the sigma embedded in M. And we call this a symplectic vanishing cycle. If the following conditions are satisfied. So first, we want this C to be transverse to the foliation everywhere besides along the core. The core just means the center of the disk times sigma, okay? And along this core, we want that the tangent bundle to C is included inside the foliation, okay? And okay, so more precisely, so now I'm going to describe how the foliation looks like and what's the compatibility condition of this induced foliation with respect to the omega, okay? Because up until now it's just a smooth condition. So we consider LR. There's some manifolds inside C of the form S1R times sigma. So this, recall, is the circle of radius R in the disk. So okay, this lives in sigma, and inside M we want it to be in a leaf. Okay, I call it FR because just the R denotes the fact that it's the leaf containing LR. Okay. And moreover, we want, so this holds for every radius up to 1, I mean, for every radius. And we want that LR is Lagrangian in the leaf. Okay, for every R smaller than, for every R bigger than 0. Okay, so this makes sense because this is n-dimensional. Okay. Okay, so this somehow it already looks okay. I'm gonna comment on this later, maybe. So the other condition, the next condition to ask is the following: is that S1R times point inside the vanishing cycle, inside the D2 times sigma. This is a point in sigma. Is contractible in the leaf where it lives, which is just FR, if and only if R is strictly smaller than 1. Okay. So for R equal 1, it is not contractible. Okay, last condition. And then I'm gonna comment on what all this mean. We want that the omega vanishes on every sphere in the leaves, FR, whenever R is smaller than 1. Okay, so we want all the leaves that intersect the vanishing cycle in the interior to be symplectically aspherical with respect to the omega that we have on the leaves. Okay. So let me comment now. Okay, this is the definition. It might seem a bit complicated, but let me demystify it. So this last condition is just technical. Okay, just because we want to use. I mean, it essentially comes from the fact that we want to use pseudo-holomorphic curves. Okay, so okay, if you know about pseudo-holomorphic curves, then this looks natural. Otherwise, just take it as it is. It's a technical condition, and that will be more clear later, hopefully. But these other 3 conditions, this should really tell you something geometrically. So, in particular, the first, so these 3 conditions are basically just saying the following. They're saying that morally, what we are asking from this C is just to be a 3-dimensional vanishing cycle stabilized by this sigma. Okay. So this is the topological description where essentially the foliation really looks like this. Looks like the product of the foliation in the 3-dimensional vanishing cycle times the sigma. Okay. Plus, we are asking the compatibility condition with omega. So we are asking that the leaves of the foliation used on C are Lagrangians in the leaves, well, these FRs. Okay. So essentially, we are exactly trying to mimic what the vanishing cycle is in dimension 3 topologically, and but using this additional structure that we have on the leaves. Okay. And yeah, another thing that to notice is that this just restricts to, well, to the 3D vanishing cycle in dimension 3. Okay. Even the technical condition here is not really important because well, in dimension 3 leaves are spherical unless they are spheres. Okay, and if they are spheres, then you know very well what's the foliation and so on. So what I'm trying to say is that this is really a definition which generalizes the three-dimensional vanishing cycle. Okay. Are there questions about this or? Okay. So then, well, let me just go into the proof of the statement. So the statement is, I recall you, is just the fact that strong symplectic foliations have no symplectic vanishing cycles. Okay. Okay. Okay, so the proof basically, so it mimics a bit what Klaus Niederkrüger did in contact geometry. He introduced the notion of Plastikstufe, which is somehow an object which obstructs strong fillability for contact manifolds in high dimensions, and it somehow, I mean, this symplectic vanishing cycle somehow resembles to the Plastikstufe introduced in the contact setting by Klaus. And well, the functioning of the proof is also similar. So for those of you who are familiar with that, this shouldn't sound like a crazy idea. So, well, we argue by contradiction. So we suppose that there is a symplectic vanishing cycle. For some sigma, okay? So this sigma is, I mean, this can be whatever. For some sigma, okay? Okay. So the idea, what's the idea of the proof? The idea is as follows. So maybe this is, yeah, it's better to do a sketch first. So we want to study certain moduli spaces of pseudo-holomorphic curves. So what we do is we look at, we pick a very well chosen leafwise, almost complex structure, J. So this means the following. So leafwise almost complex structure means that, sorry, J is an endomorphism of the bundle given by the foliation, or the vector bundle given by the foliation over M, and it squares to minus the identity. Okay. So for this kind of structure, we look at, okay, sorry, this needs to be tamed by the leafwise omega, meaning that omega evaluated on JV and V needs to be positive for every V in this tangent, in this vectors bundle minus the, I mean, minus the zero section, okay? Okay, so so we pick a very specific such structure, and then we look at we look at, okay, here one needs to prove that this is finite dimensional, smooth. I'm gonna say something about this later. Moduli space of J-holomorphic disks. Oh, sorry, this is not sigma, this is S in M. contained in leaves. So these are actually, yeah, their image is contained in a leaf, okay? So what does generalomorphic mean? Okay, so sorry, what is S? S is a Riemann surface. And what does generalomorphic mean? It means that so the Riemann surface, so it comes with a J, with a complex structure little j. And generalomorphic means that this du commutes with a j in the source and the j in the target. Okay. Okay. So we look at moduli space of this of such objects with boundary on the Lagrangians LR inside the LR inside the vanishing cycle. Okay. They don't need to be all in the same LR, but so every disk needs to have boundary in one such LR. Okay. And somehow we want to reach a contradiction by looking at this moduli space and using the properties of the symplectic vanishing cycle. Okay. Okay, and for this we need several ingredients. So I'm gonna now explain more in detail how this works. Are there questions about this sketch or? Okay. So okay, let me then start explaining more in detail. So the first step is to say that well, there is a sigma parametric family. So I'm gonna call it curly B. This stands for bishop. I'm gonna say in a second why. So the sigma parametric family of J-holomorphic disks. So J again is properly chosen here and so on. I'm not gonna talk about this too much. So in particular, in this case, well, the Riemann surface is just a disk. Okay. Yeah, sorry. Here too, actually, I already said disk, but I wrote. So it's just a disk, which I see as a Riemann surface with a J, right? The standard J. Yeah, so here we're looking at disks with values in M contained in leaves. And well, these are defined near the core. Near the core, meaning 0 times sigma inside C. Okay. So how does this family look like? Well, we can describe it very explicitly. So it looks as follows. So the neighborhood of the core looks basically like inside C. It's just a small disk. This epsilon is small. So this object lives inside C. And so I'm just going to draw a picture now. It is foliated in this way. So as it's foliated, the big disk, right? The big vanishing cycle. But now, okay, we want to describe a neighborhood of this object inside the M, okay? So how does it look like? So locally, this looks like the follows. So locally M, so locally near, yeah, this D2 epsilon times sigma. The foliating manifolds, look like, well, with omega, look like the following. So we have minus delta delta times D2, say D2 delta. So this is a delta which is a small, I mean, it's related to epsilon, of course, but I'm not gonna write it down. Times T star sigma. So this is a local neighborhood, okay? And the foliation here is just given by these two factors. So the foliation just means that first factor constant times the other two factors gives the leaves of the foliation, okay? And in fact, the structure, the symplectic structure we see is really the standard one on the disk here, comma the standard one on the cotangent bundle, okay? So it's really a split picture here. Oops, sorry. And how is this object sitting inside there? That's what we need to understand. So in fact, this object there, this factor sits as the zero section in there. And this other object sits as follows. So this is a bit this arrow here, let me write it there. This is just, I use the polar coordinates on the top disk. Maybe let me write it, sorry. Let me write it here on the sign. This is R phi goes to R square in the first coordinate, and then R phi in the disk again, okay? So let me just draw the three-dimensional situation here, forgetting about the other one, because the other one, anyways, is just a factor, an additional factor. So this picture here looks as follows. It looks like we have the leaves, which are disks like this, stacked one on top of the other. And then this embedding of the vanishing cycle looks like this. So this green stuff is the vanishing cycle. I mean, it's the D2 factor of vanishing cycle. This factor here is the minus delta delta. And this factor here, well, like that also is the D2 delta, okay? And here you can see indeed that the induced foliation on this just looks like this, just looks like concentric circles, okay? But now in this picture, this is very nice because you already see directly the holomorphic disks. The holomorphic disks are just the disks inside the leaves, which are bounded by these orange curves, okay? It's a little disk here, there's a little disk here inside, sitting inside the leaf where this orange circle lives, okay? So these are the holomorphic disks in the family, in this family that I denoted B, okay? So this family is called Bishop family because, I mean, it's similar to a family of holomorphic disks that was studied by Bishop originally for some kind of problem in complex geometry. But anyways, this is an explicit family of holomorphic disks, okay, near the core of the, so the core of the vanishing cycle essentially is I mean, blue, it's this point times sigma, okay? So this is core of C. Well, I mean, without the sigma factor, whatever that means. I mean, so this picture, I need to take it times sigma, okay? That's what it means. Okay, is this more or less okay? Or okay, now that we have this visual family of disks, well, we do what what people usually do in the non-foliated setting. Okay, here now that I say this, I can mention that I'm sweeping under the rug a lot of things, such as well, all this theory. It's very well standard for non-foliated case, like this theory of pseudo-holomorphic curves and so on. But in the foliated case, there's no reference for this, and one needs to figure out. I mean, one needs to actually prove that these moduli spaces are well defined and so on. And this is also part of the thing that we do, okay? So there's a lot of technical stuff that I'm not mentioning at all, but just to give you the idea of the geometric idea of the proof. But so then the story goes on by saying that for a generic elsewhere J, okay, so this also we can sweep under the rug a bit. This bishop family extends to a moduli space, which I denote by curly M, of disks, so which are J-holomorphic and containing leaves. And with boundary on some, I mean on one of the Lagrangians LR. Okay, so it's essentially the same kind of disks, but we have a whole. I mean, B was just essentially the local family near the core, and now we have a family which potentially we wanted to reach until the boundary of the vanishing cycle. Okay, so that's what we are actually aiming for. That's the contradiction that we're aiming for. We want to find a disk which has boundary on by using a disk in this moduli space, which has boundary in the Lagrangian L1, which is S1 1 times sigma. Okay, that's the aim, and then I'm going to explain you why this is enough also in a second. Okay, maybe not because I'm running out of time, but okay, let me tell you then a bit the logic at least. So now what we do is we look at the marked moduli space, which is made of curves where M, so this is just yeah, U lives in M and P is in S1. Okay, it's just the product of M times S1. But what's the advantage of looking at this is that we have an evaluation map to our manifold. But in fact, we know more. We know, so if we have U and P, we can evaluate U of P. But we know that these disks have boundary condition on these Lagrangians, right? And the Lagrangians live in the vanishing cycle. So actually, this evaluation map is valued in the vanishing cycle. And okay, so now that we have this, well, this okay, this stuff here up to reparameterization as dimension n+1, which is the same as the dimension of the vanishing cycle. Okay, and now the further step is the following. Okay, let me just write it in a few words. So the aim, as I said, the aim is get the contradiction by looking at the disk which has boundary on the boundary leaf, right? On the boundary of the vanishing cycle. So what we want to do now is basically we do the following. We take a curve, like an arc, sorry. So a map from say 0, 1 to the vanishing cycle. but which essentially is just T50 inside the disk times point. Okay, so it's basically just an arc going from the center of the core to the boundary of the vanishing cycle. And now what we want is, thanks to this, extract a one-dimensional subset of the moduli space. So up to perturbation, we can assume that the evaluation map is transverse to gamma, so that we can actually pull back gamma, and this is a one-dimensional moduli space. Okay, and now, now there's a bit of details that I don't have the time to explain, but one needs to study this one-dimensional moduli space and say essentially that well, this is okay, not exactly this, but the compactification so there's a notion of Gromov compactification of this, as in the non-foliatic case, which is also, so this is also further technicality. One needs to prove that you can actually compactify these moduli spaces. This is just of the form, this is just diffeomorphic to a closed interval, okay? Where 0 is a constant disk at the core, and 1 is a, well, is a possibly degenerate, meaning a nodal disk with boundary on this Lagrangian L1, which is S11 times sigma. And then one needs to actually prove that I mean, it's actually, this is not hard to see, that this boundary of this disk, let's call it U bar, is actually homotopic to S11 times point. And so this contradicts with the definition of vanishing cycle. Why is that? Well, because we have proven that S11 is a boundary of a disk inside the leaf where it lives, right? Because it bounds this disk U bar. But this was a requirement of the vanishing cycle, the fact that this does not happen, okay? We were asking that S1 cross point is contractible in the leaf where it lives if and only if the R is smaller than 1, okay? Okay, so we reached, like this, we reach a contradiction. Okay, there's a lot of things to check that you actually, this moduli space actually reaches the boundary and doesn't stop before. So that's what I swept under the rug by saying need to study. Is actually implies a lot of arguments, but yeah, this is kind of the idea of how the thing goes. Okay, so I'll stop here.
Okay, that's great. Okay, any questions?